I want you to picture a scene. It's hot. It's the Middle East. Let's say Kuwait International Airport.
Okay.
You've got that hum of the industrial air conditioning, the really harsh fluorescent lights, the long winding lines at security.
I'm with you. Not a relaxing place.
Not at all. And sitting there in the departure lounge is a man named Koos-Jan van Brouwershaven.
And judging by the story that's coming, he is probably sweating.
He is profusely sweating. Now, Koos-Jan, he's a CEO. He's a guy used to, high-pressure boardrooms, offshore deals, big money.
Right.
But right now, the source of his anxiety is sitting in his carry-on bag. It's a simple glass jar, and inside that jar is a white powder.
Which, in an international airport context, is basically the universal symbol for please arrest me immediately.
Exactly. I mean, to the untrained eye, it looks like table salt.
Sure.
To, let's say, a cynical customs officer or a drug dog, it looks like a kilo of something very, very illegal.
Yeah, that's not a conversation you want to have.
Not at all. But to Koos-Jan, it's something even harder to explain. He's sitting there just thinking, if they stop me, how do I explain that this isn't drugs? It's a battery.
Officer, I swear, this jar contains the future of the global energy transition. That'll go over well.
Right. Try telling that to a security guard who just wants to go on his lunch break. It's solid hydrogen, sir.
You're not making your flight.
You're not. You're going to a windowless room for like 3 days.
At least.
So he makes a decision. A decision that really, I think, sets the tone for this entire story we're about to dive into.
Okay.
He walks into the airport restroom, locks the stall, opens the jar, and flushes the future of clean energy down the toilet.
Oh, that hurts just to hear it. That is a lot of R&D swirling down the drain.
It is. But here is the kicker. This is the moment that matters.
Go on.
When that powder hit the water, nothing happened.
No explosion, no dramatic fizz.
Nothing. No fizz, no fire, no, toxic cloud clearing out the terminal. It dissolved. It swirled away like you were putting sugar in hot tea.
And that non-event is actually the most exciting part of the story.
That's it. Because if he had flushed a jar of gasoline,
Big problem. Fire hazard.
if he had tried to vent a canister of hydrogen gas in a toilet stall.
Catastrophe. You'd have a boom or at least a massive panic.
For sure. But it was boring.
And today, we're going to talk about why boring might be the silver bullet the energy industry has been waiting for.
Welcome to The Deep Dive. Today we are unpacking a really fascinating transcript from The New World. It's a conversation between that nervous traveler, Koos-Jan van Brouwershaven. He's the CEO of H2 Fuel and Ruud Koornstra.
And the topic is hydrogen, but not the scary, explosive Hindenburg-style gas you're thinking of.
No, we're talking about hydrogen you can hold in your hand.
Yeah.
Hydrogen in a jar.
This is one of those topics where you have to sort of suspend your disbelief for a moment.
It is.
We are so conditioned to think of energy as something inherently dangerous. Oil burns, gas explodes, lithium batteries can catch fire on planes. The idea that the solution to our massive energy crisis looks like something you'd find in your kitchen cupboard is, well, it takes some explaining.
And that's what we're here for. Our mission today is to do that explaining. We're going to break down the chemistry behind this, the magic math that makes it so efficient, and the absolutely wild business drama. And, it involves cement trucks and admirals. That made it all possible.
It's quite a story.
But let's start with the basics. Why do we even need this? We have batteries. We have wind turbines. We have solar. Why are we messing around with a white powder?
Well, it really boils down to the two things that batteries are, frankly, terrible at.
Which are?
Density and transport. Look, we are in an energy transition. We know how to generate green power. Solar panels are cheap. Wind turbines are getting more and more efficient.
The generation part is maybe not solved, but it's getting there.
It's getting there. The problem is moving that energy from where it's sunny to where it's cloudy and storing it for when the sun goes down or the wind stops blowing.
And batteries are great for your phone or maybe your car for a few hundred miles.
Right. But not for shipping energy across the ocean or powering a giant cargo ship or running a construction site for a month.
Just too heavy.
Way too heavy. They require rare earth metals. The mining is problematic, to say the least, and they leak energy over time. So the world, for decades, has looked at hydrogen.
The holy grail.
It's the lightest, most abundant element in the universe. It packs a huge punch, but traditional hydrogen is just a complete nightmare to move.
Yeah, my mind immediately goes to the Hindenburg.
And that's the image everyone has. But even on a practical level, to move hydrogen, you have to compress it to, what, 700 bar?
That's 700 times atmospheric pressure.
An incredible amount of pressure. Or you have to freeze it to near absolute zero to make it a liquid.
Both of which take a massive amount of energy just to do the compressing or the freezing.
Exactly. You lose a huge chunk of your energy just preparing it for transport. And it requires specialized, heavy, and frankly, dangerous tanks.
So the industry has been stuck for a while. We want the benefits of hydrogen, but we hate the logistics.
We hate moving it. So, enter the white powder, Cusian solution. The chemical name is sodium borohydride.
Okay, let's get into the weeds here. Sodium borohydride. I'm having some high school chemistry flashbacks.
Yeah.
What exactly is this stuff?
The chemical formula is NaBH4,
Yeah.
and I think the easiest way to think of it is as a locking mechanism, a molecular cage.
A cage.
Yeah. Just as hydrogen is safely locked away inside a water molecule H2O and it doesn't, burn you when you take a shower,
Truthfully.
hydrogen can be locked just as safely inside this salt-like crystal structure.
So what's doing the locking?
You have boron, which is the B, and
Yeah.
sodium, Dan, and they're essentially holding on to 4 hydrogen atoms, the H4, and they hold on tight.
Okay.
In this solid powder form, the hydrogen is completely inert. It's stable. It doesn't want to leave. You can heat it up. You can shake it. You can flush it down an airport toilet. It stays locked.
And this is the complete opposite of hydrogen gas.
The polar opposite. Hydrogen gas is basically the Houdini of elements. It's tiny. It leaks through solid steel. It causes something called hydrogen embrittlement, which weakens metals.
It's always trying to escape.
Always. But in the salt form, it just sits there. It's patient. To get the energy out, to unlock that cage, you need a very specific key.
And that key is just water.
Well, yes and no. It's water and a catalyst. And this is where we have to talk about the Mentos and Cola moment.
I loved this analogy in the source material
Yeah.
because we've all done it, or at least seen it on YouTube. You drop a Mentos Mint into a bottle of Diet Coke.
And whoosh, an immediate chaotic release of gas. A geyser of foam.
Right, it's a completely uncontrolled reaction.
Physics just takes over. The surface of the mint creates nucleation sites, the dissolved CO2 comes out of solution, and everything happens at once. It's a mess.
And that's what happened with the early attempts at this technology, right?
Yeah.
Cusian mentioned in the interview that the Americans tried this under the George W. Bush administration.
They did. It was part of an initiative called Freedom Energy. The U.S. military was very interested. They wanted to run submarines on this powder.
That makes sense. Silent, no emissions, very dense fuel. Perfect for a submarine.
The idea was perfect on paper, but they couldn't control the fizz.
They got the Mentos guys.
They got the geyser, exactly. They would mix the powder in the water, and the reaction would just run away from them.
So, too much hydrogen all at once.
Either too much, too fast, which would cause temperatures to spike, or the reaction would just stall out and die. It was completely unstable. And you can't run a nuclear submarine if your engine is acting like a science fair volcano.
So the project failed. They gave up on it.
They did. And the idea just sat there for years. So how did we get from failed U.S. military experiment to Cusian flushing it safely down a toilet in Kuwait?
This is where the story gets really good.
This is where it takes a beautiful, unexpected turn. The solution didn't come from a nuclear physicist at MIT or a rocket scientist at NASA.
No.
It came from a man named Gerard Luchtehide.
Luchtehide, which is a great Dutch name.
It actually means lightness or airiness, which is very fitting for this story.
It is.
And Gerard wasn't an energy guy. He was a medical device inventor. He worked at the Sophia Children's Hospital in Rotterdam.
Okay, now that is a pivot. What on earth does a children's hospital have to do with creating a new form of hydrogen fuel?
Well, Gerard's specialty was creating inhalers for children with very severe lung conditions, like cystic fibrosis.
Ah.
Now think about that. If you are designing a device to deliver life-saving medication into the delicate lungs of a sick child, you need absolute unwavering precision.
Right, you can't just blast it in there.
No, you need to mix the medicine with air perfectly at the exact right rate every single time. You can't have a geyser. You can't have a misfire. It has to be controlled.
So he was an expert in controlled mixing and dosing.
At a micro level.
Yeah.
So he looked at the sodium borohydride problem, the Mentos problem, and he didn't see an energy problem.
He saw a dosing problem.
He saw a dosing problem. He realized the Americans had been using regular water, which has all sorts of ions and impurities. He figured out that if you use ultra-pure water that's been deionized, stripped of everything, completely neutral, the reaction doesn't start on its own.
Okay, so the ultra-pure water is the safety switch.
It's the blank canvas. It won't react with the powder by itself. Then he adds a specific proprietary catalyst, that's the trigger, in tiny, precise microdoses.
Like with the inhaler.
Just like with the inhaler. By controlling the purity of the water and the amount of catalyst he adds, he essentially created a throttle. He could speed the reaction up, slow it down, or stop it instantly just by cutting off the catalyst.
He tamed the Mentos.
He tames the Mentos. He turned a chaotic fizz into a controllable fuel line. But in doing so, he unlocked a feature of this chemistry that is arguably even more important than the control itself.
Oh, okay.
And this is the part where I need you to bear with me on the math, because it sounds completely impossible at first.
The double hydrogen bonus.
Yeah.
I admit, I read this part of the transcript 3 times. I thought that was a typo.
It sounds like a perpetual motion machine or some kind of late-night infomercial scam.
It does. It sounds like buy one hydrogen molecule, get one free.
It does sound like that, but it's just stoichiometry. It's just basic chemistry.
So walk us through it slowly, because if I'm a listener right now, I'm probably pretty skeptical.
Totally understandable. So let's visualize the atoms again. You have the fuel powder, NaBH4.
Right.
That one molecule contains 4 hydrogen atoms, the H4.
Check. 4 hydrogens locked in the salt,
To release them, you mix it with water, H2O.
which has 2 hydrogen atoms.
Correct. Now, in most chemical reactions, the water is just a solvent. It's just the liquid swimming pool that the reaction happens in. But here, the water is an active participant.
Okay.
The catalyst, in a way, is so powerful that it splits the water molecules at the same time it unlocks the salt molecules.
So you aren't just harvesting the hydrogen from the powder.
No, that's the whole point. You are harvesting the hydrogen from the water, too.
So let's do the math.
The balanced chemical equation shows that for every 1 mole of the powder, you react it with 2 moles of water.
2 H2O molecules.
The result is that you get 8 atoms of hydrogen gas out,
So 4 from the NaBH4.
and 4 from the 2 H2O molecules.
You get 8 out.
You put in 4 units of stored transportable hydrogen, and you get 8 units of usable hydrogen gas at the point of use.
That feels like cheating the laws of physics.
It feels like magic, but it's not creating energy from nothing. You're just unlocking the chemical energy that was already present in the water. But think about the logistics of that.
It changes everything.
If you are a truck driver and you need to deliver 100 units of energy to a construction site in the form of hydrogen, with this system, you only need to load 50 units of powder onto your truck.
Because the other 50 units of energy are waiting for you in the water tank at the construction site.
Precisely. You are literally fueling your machine with the water from a tap as much as you are from the fuel you brought with you. You have effectively doubled the energy density of your entire transport operation.
That is just, it's wild. It completely changes the economics. You're shipping half the weight, half the volume.
And weight and volume are money in logistics. Let's really break down the density comparison because the numbers here are stark.
Yeah, the source mentioned diesel and compressed gas. Give us the tail of the tape.
Okay, so diesel is the gold standard for energy density, right? It's heavy, it packs a lot of energy into a small space. That's why it's so hard to replace.
Right.
This powder, when packed, has about 86% of the volumetric energy density of diesel.
86%. That's incredible.
It's shockingly high for a clean fuel. Usually when we talk about batteries, you're talking about something that's maybe 10 or 20 times worse than diesel by weight.
Or even more.
Right. So this is almost as good as oil. Now let's compare it to hydrogen gas. If you see one of those big tube trailers on the highway, the trucks with the really long, heavy steel cylinders.
Yeah, I know the ones. They look like a giant cigar pack on wheels.
That's the one. They are carrying compressed hydrogen gas at, say, 300 or 500 bar. That massive truck, which weighs a ton, is carrying about 500 kilograms of actual hydrogen.
500 kilos. That's it. For that whole truck.
That's it. It's mostly steel tank and just empty space between the gas molecules.
Wow.
Now, take a standard 20-foot shipping container, nothing special, the kind you see on a cargo ship.
Yep.
Fill it with this powder. You are now carrying the equivalent of 5,000 kilograms of hydrogen.
So, let me get this straight. 1 truck of powder does the work of 10 trucks of compressed gas.
Correct. A 10x improvement in transport efficiency.
That's not an incremental step. That's a revolution.
It's a leap. And this is the crucial part. The powder truck isn't a bomb. The gas truck is a highly pressurized, flammable object. If it crashes, it's a major event. You shut down the highway. The powder truck, it's just carrying salt. It's at ambient pressure. You can transport it on a standard flatbed truck, a train, a barge. It's just cargo.
You don't need a national network of high-pressure hydrogen pipelines.
No.
You just need Amazon Prime. You just need boxes.
That's the drop-in nature of this technology. It fits into the logistics infrastructure that we already have. It doesn't require rebuilding the world.
We briefly touched on safety with the toilet story, but I want to go back to that regular water experiment because it's really important. Kustian talks about what happens when you just mix the powder with regular tap water.
This is so important for the permitting and for, public acceptance. If you're on a ship and a bag of this stuff spills on the deck and it starts raining, what happens?
Right. Do you have to evacuate the port?
Exactly, and the answer is no. Kustian says if you mix it with regular tap water, which has ions and isn't ultra-pure, and you don't add the catalyst, it just fizzes, very slightly.
Like an aspirin?
He says it's like an aspirin or an Alka-Seltzer tablet. It slowly degrades over a long period. It doesn't explode. It doesn't rapidly release all its gas. It just becomes a slightly fizzy, basic solution.
And this is why he could flush it.
This is exactly why he could flush it. It proves that without the specific key, the reactor with the ultra-pure water and the catalyst, the energy stays safely locked away.
So let's recap. We have a fuel that is safe, incredibly dense, easy to transport using existing infrastructure, and it doubles its energy output on site by using local water.
Pretty much.
It sounds too good to be true. Where are they actually using it? Is this still just a lab trick, or are there real machines running on this powder today?
They are moving out of the lab and into the real world. The flagship project, the one they talk about the most, is a boat called the Neo-Orbis.
Neo-Orbis.
It's a 19-meter vessel, so a decent size, and it's being built for the Port of Amsterdam.
What kind of boat? A patrol boat or a tour boat?
Sort of a multi-purpose port authority vessel. Now, ships, especially smaller ones, are one of the hardest things to decarbonize.
Why is that?
Water creates a lot of drag. Drag requires a lot of power. If you try to put enough batteries on a ship to give it a decent range, the batteries themselves are so heavy.
They make the ship sit lower in the water.
Exactly. Which creates more drag, which requires more power, which requires more batteries.
You get stuck in this battery weight spiral.
That's a perfect way to put it. So for the Neo-Orbis, they are using the H2 fuel reactor as a range extender.
So it's a hybrid system.
It's a hybrid. The boat has a battery pack that runs the electric motor for propulsion, but it also carries the powder and the reactor. As the boat is sailing along, the reactor is gently mixing the powder and water, making hydrogen,
which feeds a fuel cell,
which recharges the battery while the boat is moving.
So it's basically like a Toyota Prius, but instead of a little gasoline engine kicking in to charge the battery, it's a salt reactor.
That is the perfect analogy. It completely solves the range anxiety for maritime applications. They're also looking very seriously at construction sites.
Oh, this is the famous nitrogen crisis in the Netherlands.
If you live in Europe, especially the Netherlands, you know this pain. Major construction projects, highways, housing developments are being halted because the diesel generators and trucks produce nitrogen oxides on rocks.
And they violate the EU's environmental rules. You literally can't get a permit to build.
Correct. And the problem is the electric grid is often too weak at a new construction site to plug in all your heavy machinery, your cranes, your excavators.
You're stuck.
You're stuck. So H2 Fuel says, we just drop one of our containers on the site.
The power plant in a box.
The power plant in a box. It has the powder, the reactor, a fuel cell. It produces silent, clean electricity 24/7. You charge your electric excavators overnight from the container. No nitrogen, no noise pollution, no diesel fumes.
And what about data centers? That seems like a huge market.
That's the big whale. Data centers for companies like Google, Amazon, Microsoft consume absolutely massive amounts of power, and they need 100% uptime. If the grid fails, everything goes down.
So they have backup generators.
Huge arrays of diesel generators, and they hate it. It's dirty, it's noisy, and it ruins their corporate carbon footprint.
They spend billions marketing how green they are, and then they have a diesel generator in the back.
Exactly. This powder could replace those diesel backups with clean, long-duration storage. The powder can sit there for 10 years without degrading, unlike batteries, which lose charge, and then be ready to go at a moment's notice.
Okay, so the applications are clear, they're obvious. Ships, construction, backup power. But, and you knew this was coming, there's always a but in these deep dives.
Always.
We have to talk about the catch. Because nothing in thermodynamics is free. There's no free lunch.
The catch is the waste, the leftovers.
The spent fuel.
Right. When you run this reaction, the hydrogen leaves the reactor to go power the fuel cell, but you are left with the cage. The boron and the sodium are still there, now mixed with oxygen from the water. It forms a residual liquid, a slurry, called sodium metaborate.
Slurry is never a pretty word in engineering.
It's not. It's a thick, white sort of goo. Chemically, it's basically borax, the stuff you use in laundry.
So it's not toxic or radioactive like nuclear waste?
No, not at all. It's very safe. But you have a tank full of it. And the big criticism of this technology has always been, great, you got useful energy out, but how much energy does it take to turn that goo back into the magic powder?
The round-trip efficiency. How much do you lose in the recycling process?
And exactly. You have to recycle it. You have to break those chemical bonds and reset the crystal structure. And for a long, long time, the math looked terrible.
This was the original process they developed.
Yes, the original process which they worked on with the University of Amsterdam was a purely chemical recycling method.
Okay, give us the bad news. What were the numbers on that?
To create enough powder to hold 1 kilogram of hydrogen's worth of energy, which is about 33 kilowatt-hours of potential energy, you had to put in about 330 kilowatt-hours of electrical energy to recycle the waste slurry.
Whoa, wait, let me process that. You're putting in 330 kilowatt-hours to get 33 kilowatt-hours back out.
Correct. A 10-to-1 ratio.
That's not a fuel cycle. That's an energy incinerator.
Right.
Why on earth would anyone do that? That seems incredibly wasteful.
Well, Kustion had a geographical argument for it, a very specific one. He called it exporting sunshine.
Exporting sunshine.
His argument was, look, if I do this recycling process in the middle of the desert in Saudi Arabia or Namibia or Chile, where new solar power costs maybe 1 cent per kilowatt hour, and the sun is effectively infinite and free,
And the efficiency doesn't matter as much.
then maybe the inefficiency doesn't matter. The cost of the input energy is so low that it's still profitable.
So it's an energy arbitrage play. You take virtually free, but stranded, energy from the desert, you bottle it in this powder with 90% loss, and then you ship it to drizzly, expensive Northern Europe where energy costs 30 cents per kilowatt.
That was the pitch. We are bottling sunlight. And strictly speaking, on a spreadsheet, it works economically if the input energy is cheap enough.
But from an engineering standpoint,
It's ugly. 10-to-1 is just hard to swallow. It felt fundamentally wasteful, and it kept a lot of serious investors away.
okay, and this is where the story gets really interesting. This is the plot twist. Because there was another company sniffing around this tech, right?
There was a rival, the Flexgroep.
The cement guys.
The cement guys, this is what I love about real innovation. It doesn't always happen in a sterile white coat lab. The Flexgroep, based in a town called Etten-Leur, started out as a logistics company.
They moved cement powder.
Exactly. They transported dry bulk materials like cement,
So?
which is a powder that is notoriously difficult to handle. If it gets even a little bit wet, it hardens and ruins your truck.
So they were experts in keeping powders dry and moving them efficiently.
They were world-class experts in dry powder logistics. And they were looking at this hydrogen powder idea too, but from a trucking and handling perspective.
And the source material says H2 Fuel and Flexgroep were in a bit of a Cold War.
That's how Kustion described it. They were circling each other. H2 Fuel had the patents for the reactor. Flexgroep was working on the logistics for that Neo Orbis boat. They were frenemies.
Okay.
And while H2 Fuel was trying to solve that terrible 10-to-1 recycling problem with more and more complex chemistry dissolving the slurry with acids and solvents, the Flexgroep guys started tinkering in their garage.
They weren't just truck drivers, they were hands-on inventors.
They were, and they looked at that slurry and they thought, why are we dissolving everything? That's a chemical change and it takes so much energy. Why don't we just try to separate the crystals physically?
Mechanical separation instead of chemical.
Exactly. I started thinking like cement guys, not chemists. They developed a proprietary method to mechanically separate the sodium metaborate crystals from the water using physical processes. They didn't fight the chemistry, they just used physics.
Like a centrifuge or a filter press, but way more advanced.
Something along those lines. And what did that do to the energy math? That ugly 330 kilowatt-hour number.
It must have changed it.
It collapsed it. The Flexgroup's mechanical method, almost overnight, dropped the energy requirement from 330 kilowatt down to 140 kilowatt.
That's huge. That's more than a 50% reduction instantly.
It's massive. It goes from a 10-to-1 ratio to more like a 4-to-1 ratio. Still not perfect, but suddenly in the realm of viability.
And that wasn't the end of it.
No. They believe they have a clear engineered path to get it down to 40 kilowatts.
Wait, 40? Let's do the math on that again. If they hit 40 kilowatts input to recycle, and you get 33 kilowatts of usable energy back out,
then you are almost at a 1-to-1 ratio. You're putting in about 1.2 units of energy to get 1 unit back out.
At that point, the inefficiency argument completely evaporates.
It's gone. At that point, you are competitive with almost any other form of energy storage, like pumped hydro or compressed air, but you have all the added benefits of safety, density, and transportability.
That is the game changer.
It is the absolute holy grail for this technology, and this realization, this breakthrough, it ended the Cold War.
They stopped fighting each other.
Kusyan said he had a choice. He could keep fighting for his own chemical process and probably die in the Valley of Death, or he could merge with the truck drivers from Etten and actually get this thing to market.
So they merged.
As of January 1st this year, they merged. H2 Fuel and Flexgroep are now one company.
1 + 1 = 3.
It's a perfect example of that. H2 Fuel brought the high-tech reactor and the core chemical patents. Flex brought the blue-collar logistics know-how and, most importantly, the recycling breakthrough. It's a perfect marriage of science and supply chain.
You mentioned the Valley of Death just now. That sounds ominous.
It's a term from the startup world, and it is the place where most revolutionary technologies die.
What is it exactly?
It's that gap between I have a working prototype in my lab that proves the science works, and I have a full-scale factory that is producing this reliably and economically.
Scaling gap.
Crossing that gap takes money, a lot of money, and it takes risk. And this is where Kusyan gets quite passionate and frankly frustrated in the interview. He talks about dealing with the banking system and the government.
This is the subsidy paradox you mentioned.
Right. He gives this perfect example. He points out that a company like Shell, which makes billions and billions in profit, gets a $150 million government subsidy to build a new hydrogen electrolyzer.
Why? I mean, they obviously have the money.
Because they are a safe bet. They have a massive balance sheet. The government official who signs that check knows that Shell won't go bankrupt next week. Their job is safe.
Okay.
But H2 Fuel, they have been losing money for 18 years, pouring everything into R&D to develop this technology. They have a negative balance sheet.
So when they go to the government and ask for a subsidy,
the government says, sorry, you're too risky. We can't give taxpayers money to a company that might fail. That would be illegal state aid.
It's the classic, you need a job to get a car, but you need a car to get a job trap. The system is designed to support the incumbents, the old guard, while the actual disruptors starve for cash.
It favors slow, safe evolution, not risky revolution. And this brings us to the Admiral.
Oh, I love this story. Admiral Jan Willem Kelder. This is a real highlight of the transcript for me.
Jan Willem Kelder was a former commander of the Royal Netherlands Navy, and he was a big supporter of H2 Fuel. He sadly passed away recently, but his philosophy still drives the company.
What was his story?
He used to tell this story about his time commanding a warship, the HNLMS Trump. He said he had a shelf in his captain's cabin, and it was filled with rule books.
The Book of Rules.
Exactly. Rules from the Dutch government, from NATO, from the UN, from the sailors' unions, from the environmental agencies. And he said that, basically, if you read all those rules, they added up to one thing. You cannot do anything.
Paralysis by regulation.
Complete paralysis. Every possible action is forbidden by some subclause in some book. But then he says, imagine I get an order from the top. The order is simple: save the princess. That is my mission.
Okay.
To save the princess, I have to break the rules. I have to speed, or enter foreign waters I'm not supposed to, or launch a helicopter in bad weather. I have to take a risk.
The Save the Princess protocol. I love it.
Exactly. And his point was this: if I break the rules and I save the princess, I become an admiral. I'm a hero. I get a medal. But if I break the rules and I fail,
you're court-martialed.
I get court-martialed. I lose my pension. I'm disgraced. My career is over.
So the incentive structure is completely broken. There's a huge upside, but the downside is total ruin.
That was his powerful critique of modern leadership. He said that today's bankers, politicians, and corporate CEOs are all terrified of the court-martial.
They're afraid of losing their spot.
They're terrified of losing their pension and their reputation. So when they are faced with a choice between saving the princess, which could mean fixing the climate or funding a breakthrough technology, and following the rules, which means protecting their own position, they almost always choose the rules.
They let the princess die to save their career.
It's a brutal way to put it, but it's accurate.
Mm-hmm.
Kusian argues that the energy transition is stalled because we lack admirals. We have a world full of managers and not enough commanders who are willing to take that save the princess risk.
And the regulations themselves are a huge part of this problem. He mentioned the transport laws specifically.
Oh, it's Kafkaesque. It's completely absurd. The laws for transporting hydrogen are in some cases 25 to 50 years old. They were written for high-pressure explosive gas. They assume hydrogen is a bomb.
And the rulebook has no category for a safe, inert powder.
None. He said he's been in meetings with bureaucrats who smile politely and say, "Sir, the rules clearly state you cannot transport hydrogen in this way, so you must stop."
And he says, but this isn't gas.
And they say, "But the label on the jar says hydrogen, so it must follow the rules for hydrogen." It's a complete computer says no situation.
They can't get their heads around it.
Some can't. He says he's had to fight these long battles where a few enlightened people finally realized, wait a minute, there can't be rules for something that hasn't been invented yet. But until that rule is officially changed, the bank won't lend the money and the insurance company won't insure the cargo.
It's the valley of death, but it's made of paper and red tape.
It is. And that is why Kusian's personal story is actually really relevant here. He wasn't always a struggling startup guy.
Right, he was a big shot.
He was the CEO of Hirma, a massive offshore construction company. He was the man. He had the big salary, the corner office, the golden handcuffs.
He was the guy who could have just coasted to retirement, following the rules.
He absolutely could have, but he left. He walked away from it all. He said he wanted to do something that actually changes the system, not just optimizes the old one. He traded the security of the old world for the stress and uncertainty of the new world. And that takes the kind of admiral courage he was talking about.
So how are they planning to break out of this valley of death? What is the new strategy now that they've merged with Flex and have the recycling tech? I heard they aren't trying to build everything themselves anymore.
That's right. The strategy is focus. In the past, they admit they made the mistake of trying to do too much. They were trying to design the boat and design a car, design the whole supply chain.
It was spread too thin.
Way too thin. So now they are focusing on building one thing and one thing only. The container.
The standard 20-foot shipping container we talked about earlier.
It's the Lego brick of global trade. Everyone understands it. H2 Fuel is now building a self-contained power container. It's a mobile plug-and-play unit.
So what's inside the box?
Inside, you have the reactor that Gerard Lukta had designed. You have the storage for the powder fuel. You have a small tank for the ultra-pure water. You have the fuel cell to make electricity. And you have a small battery buffer and all the smart electronics.
So it's a complete power plant in a box.
It is a decentralized power plant in a box. You don't build new infrastructure, you just drop the box.
Yeah.
You drop it at a gas station to power a new bank of EV superchargers without digging up the street to upgrade the grid.
You drop it at a festival for clean power.
You drop it at a hospital for foolproof backup.
It's decentralized. That's the key word.
This is the core of their new vision, power to the people. You are cutting the cord to the centralized grid, and this touches on a massive, almost criminal inefficiency in our current system that Ruud Krinstra brought up in the interview.
The wasted wind energy.
Yeah.
This statistic absolutely blew my mind. The official term is curtailment.
It is painful to even think about. In the year 2024, the Netherlands they curtailed 3 gigawatts of perfectly good wind energy.
Threw it away. How do you throw away wind? I don't understand.
The grid was full. The copper cables couldn't handle all the power being generated on a windy day. So the grid operators literally called the wind farms and said, "Turn off your turbines. We can't take your power. Stop producing."
3 gigawatts. That's like, what, 3 large nuclear power plants worth of energy.
Roughly, yes. Just vanished into thin air. Wasted potential. Gone forever.
And Kustian's point is, if we had these containers...
If we had a few dozen of these H2 fuel containers sitting right next to those wind farms, we would not have turned the turbines off.
No.
We would have used that trash energy, that free excess electricity, to run the recycling process. We would have turned that wasted wind into jars of hydrogen powder.
You store the value instead of throwing it away. You're creating a physical asset.
Precisely. That is the ultimate holy grail. It turns intermittent, use-it-or-lose-it renewable energy into a permanent, stable, shippable fuel. You are essentially freezing the wind in time inside a crystal, and you can use it 6 months later in a different country.
So let's pull it all together. We have the technology refined from a children's hospital. We have the recycling breakthrough from the cement guys. We have the new power container strategy. It really feels like they are right on the edge of a major breakthrough.
They are. They are at that critical point. They need that first big industrial scale success. They need to show the world not just a lab report or a prototype boat, but a fleet of working containers powering real businesses, saving them money, and solving their energy problems. Once that happens, the floodgates of investment could open.
It's such a classic story of innovation, isn't it? It's never just about the science. It's almost the easy part. It's about the grit, the logistics, the funding battles, and the long, hard fight against the inertia of the status quo.
And sometimes it's about having the nerve to flush a jar of your life's work down a toilet in Kuwait when you have to.
Absolutely. As we wrap up here, just looking at this whole story, from the children's hospital inhaler to the cement trucks to the admiral saving the princess, and I'm really struck by how messy and interconnected it all is.
It really is. We tend to think of the energy transition as this clean, monolithic thing, neat rows of solar panels and sleek Teslas. But the real revolution, the stuff that will actually change the world, might be happening in these weird niche intersections. Medical tech meets logistics meets chemistry.
So what's the big takeaway for you when you step back and look at the whole H2 fuel story?
For me, it's a powerful reminder that the solutions to our biggest problems often already exist. We aren't really waiting for some new law of physics to be discovered in a lab. The miracle is already sitting in a jar. The real barriers are paperwork, risk aversion, and old habits. The physics works, the chemistry works. The question is, do we as a society have the admiral's courage to rewrite the rules to let it happen?
That's a powerful thought to end on. And I'll leave our listeners with one more provocation to chew on, building on that idea. We've spent so much time and energy worrying about the grid. Is it stable? Is it green? Is it getting too expensive? But just imagine for a second a world where you don't need the grid at all.
Yeah.
Imagine if, once a year, a truck pulls up to your house, just a normal delivery truck, and it drops off a pallet of what looks like salt bags. You dump them into a hopper in your basement, kind of like an old coal chute, and that system runs your entire house for the next 12 months. Heat, light, your car charger, your internet, everything.
Wow.
No monthly utility bill, no blackouts during a storm, no dependence on giant, aging power lines. If you could power your entire life with a yearly delivery of salt, would you ever connect to the grid again?
That is true energy independence. And looking at this powder, it's really not as far away as we might think.
Something to think about next time you pick up a salt shaker at dinner.
Thanks for listening to The Deep Dive. We'll see you next time.
Take care.